This is the second series. The previous lecture contents we were discussing about the structure of nuclei, like the neutron, proton, we already discussed, and we also discussed about the nomenclature like isobar, isotopes, those things. And we started with property of nuclei, and in that we just started nuclear charge, which is nothing but Z into E, and then radius. For you to recall, R equal to R naught a power 1 by 3, and nuclear density. Up to that we were discussing, and we will just continue today with further properties of nuclei, namely mass, binding energy and stability of nuclei, angular momentum and spin, and magnetic moment of nuclei. And we already started with nuclear mass. We will just recall that, and we will continue. The nuclear mass is always expressed in atomic mass unit. And what is one atomic mass? AMU is atomic mass unit. It is 1.66 into 10 power minus 27 kilogram. That is the unit. Helium, if you take helium atom, that is alpha particle, helium-24 has got 2 proton, 2 neutron. So what we generally expect is the mass should have, the mass of helium-24 must be equal to mass of 2 neutron plus mass of 2 proton. But that was not happening, that was not true. We find that mass of the nuclide MaZ, we just write as MaZ for mass of nuclei, is always mass of the nuclide MaZ is less than Z times Mp plus A minus Z Mn. So it is not equal. So the mass of the nucleus is always less than the mass of the constituting nucleons. In the case we discussed for the alpha particle, it has got 2 neutron and 2 proton. So what we expect is, or put all the mass together, that must be the mass of helium atom, but that was not. So there is always a mass defect. When the nucleons combine, they lose mass. There is a mass defect, and that is, we denote that as delta M, mass defect delta M. Now we have got different mass spectrometers like Aston mass spectrograph, Bainbridge, all of them reported only mass defect. So we didn't get the masses that we expect. So this was not understood until Einstein's mass energy relation. So Einstein was the first person to tell that mass is not conserved. Mass can appear as energy, or energy can appear as mass. So there is no mass conservation, and there is only energy is conserved, only energy is conserved. Therefore, mass is just manifestation of energy. So energy is the manifestation of that energy is mass. When the mass decreases, it appears as energy, and this is a famous equation, Einstein's relation, E equal to mc squared. And just to tell you something related to this E equal to mc squared was derived in 1905, and therefore 2005 was World Year of Physics. We celebrated that World Year of Physics, and that is really a breakthrough. After that, our understanding of nuclear structure is very much different. So now what we see is, when the mass decreases, energy appears. Therefore, we can say that binding energy Be, we have written the binding energy Be equal to delta M c squared. What is that delta M? Delta M is change in mass, mass defect. That is equal to delta M c squared. So when there is a small mass defect, it appears as binding energy. So we have to just put this equation 2 in 1, and I get that equation 3, namely MaZ is equal to Z times Mp plus A minus Z Mn minus binding energy. So that is a defect, that the defect part appears as energy. So this is the energy mass formula, and this is a starting of a mass formula, and here the masses are in MeV. See, the AMU, one atomic mass unit, is expressed in MeV. 1 AMU, because energy and mass are related, and therefore we will just see, if it is one atomic mass unit, what is the energy equivalent of that. So we will just go to that Einstein's relation, E equal to mc squared, and then we will just put one atomic mass unit, which is nothing but 1.66 into 10 power minus 27 kilogram. This is m, that the mass we get, into this is 9 into 16. What is that 9 into 16? Velocity of light is 3 into 10 power 8. So, when you square that, we get 9 into 10 power 16. So, it is all in MKS unit, therefore, we will be getting in joules. So, if you multiply this, we will be getting this energy equal to 14.94 into 10 power minus 11 joule, or we can write that as that in EV, because in nuclear physics we do not talk about in joules. We the convention is we used EV, electron volt, as the energy. Now, how is electron volt and joule connected? That is the last expression we have shown. 1 EV, that is 1 electron volt, is equal to 1.6 into 10 power minus 19 joule. That is because this electronic charge is 1.6 into minus 19 coulomb. So, that coulomb into voltage is nothing but energy. So, we get this expression. Now, we will write the expression in terms of, therefore, 1 joule will be 1 EV by 1.6 into 10 power minus 19. Therefore, already the expression we had in joule. So, we are just substituting there, and we are getting E is equal to 1.6, this part, 9 into 10 power 6, that is from the previous equation, and this part is written. So, we are getting the energy in EV. See, here again in atomic case, EV is sufficient, that energy is suitable, because for example, the excitation energy of hydrogen atom, it is 13 EV. So, 13 EV, all the EV energy will be in the atomic case. When you go inside the nucleus, the energy will be in MeV, that is 10 power 6 times larger. The energy will be in MeV. And to just to tell you the on the same line, if you go inside a particle, that is neutron, if you want to break a neutron or break a proton, the energy required will be GeV. That is what we had in that hadron collision. So, the people were in CERN, they were having proton and neutron, they are called hadron. When you say hadron, high energy particles. So, GeV energy they bombarded. So, we have got atomic case EV, nuclear case MeV, and particle, that is called particle physics. When you go into particle physics, it is in GeV. Now, here we will come back to what we were discussing. We said EV, therefore, that is 931 into 10 power 8 EV. What is convenient here is MeV for nuclear physics. Therefore, we just write the expression as 9.31 into 10 power 6 EV. The 10 power 6 is written as MeV. Therefore, 931 MeV is easy to remember. So, what we have found out now is, what we have derived now is, energy 1 atomic mass unit is equal to 931 MeV. This you can always remember, because in many application problem, nuclear physics problem, this has to be used. Therefore, you remember 1 atomic mass unit is equal to so much of energy, and therefore, in equation 3 all terms are in MeV. We will go to that equation 3, that is I will go back to equation 3. See, in this equation 3, you may wonder, left side is mass, here I get Z is mere number, this is mass, A minus Z is a mere number, the Mn is mass, this is energy. So, in an equation I can't put one energy and mass together. Therefore, the masses are expressed in energy and we get energy. So, on the left hand side it is energy, right hand side is also energy. Therefore, the equation is valid. Now, binding energy and stability. Naturally, when the binding energy is large, stability is large. You can't easily break that nucleus. So, what they found is, they found out experimentally, they determined the binding energy of different nuclei, like starting with hydrogen and then helium, beryllium, carbon. So, they took different elements up to uranium. So, take all the elements and they have found out what is the binding energy, experimental binding energy, using some experimental method. And in the x axis we have mass number A, and the y axis we have binding energy per nucleon. This is the experimentally observed curve. Experimentally observed, the red curve is experimentally observed curve. What we observe is very light nuclei have got low binding energy per nucleon. whereas light nuclei have got low energy. Similarly, very heavy nuclei has got low energy. Intermediate we will find binding energy is maximum. So, naturally the natural process what will happen is, if it is a very heavy nucleus, it wants to become more binding energy. It has to attain a state of larger energy, larger binding energy. Therefore, so it is like, see, suppose we have got a valley, in that some stones are kept everywhere. Those stones which are away from the valley, up the valley, will always, if you slightly disturb, they will be having the tendency to come to the bottom. At the bottom, binding energy is large, because it is bound to the earth. Suppose they are already at the bottom, it becomes more stable, Those on the upper side of the valley are unstable, relatively unstable. Similarly, here we have stability is when the binding energy is maximum. We find that about iron, in that region, binding energy per nucleon is maximum, which means iron is very stable, one of the stable elements. And if you go to the other side, uranium, it is unstable, the binding energy is slightly lower. Therefore, if we slightly disturb, it will try to become intermediate mass nuclei. See, the iron is an intermediate mass nuclei. Tin, Sn, that is also an intermediate mass nuclei. And uranium 238 is a heavy nuclei. And when you go to this side, like a helium, hydrogen, those are all light nuclei. Therefore, this uranium will have a tendency to become, so this heavy nuclei, and this is light nuclei, and this is intermediate mass nuclei. So, all the heavy nuclei will have a tendency to go towards intermediate mass nuclei. Therefore, what will happen? They will undergo fission. So, they will break into two, so that the fragment nuclei will be intermediate mass. So, that is the fission process. Fission gives energy, that the difference in binding energy is given as energy. So, the uranium heavy nucleus will want to become intermediate mass nuclei. Therefore, fission gives energy. The difference in binding energy will be released as energy. And similarly, we have got fusion. Light nuclei will have a tendency to fuse. So, the fusion will take place. Now, we know that fusion is taking place in star. In all the stars, including sun, thermonuclear reactions are taking place. Fusion. They are all fusion reactions which are liberating a large amount of energy. Similarly, we have got the fission process. Uranium will undergo fission, and the resulting fragments will be more stable. So, the energy released will be there. So, for example, since we have been talking about MEV, just an idea you remember, a fission process, a single fission gives about 200 MeV energy, and if you take fusion, a single fusion will give about 25 MeV energy. Now, we will go to next topic in the syllabus, angular momentum and spin. We know linear momentum. Linear momentum is mass into velocity is linear momentum. Now, moment of linear momentum is angular momentum. What do you mean by moment of? When you say moment of, it is any quantity. Suppose I take a quantity f. Moment of f is f cross r. That is cross product into the r, the distance r. If you take some quantity L, so L cross r, that will be the momentum. Here it is moment of linear momentum, that is mv cross r. mv cross r. mv is the linear momentum, cross r, that is angular momentum. So, that is equal to LH cross. Here again, Planck found out that is LH is the Planck's constant. Planck found out that the microscopic level, in the atomic and nuclear level, angular momentum is quantized. Suppose I take a top. So, the angular momentum is not quantized. First, initially when you are pulling the string, it will move very fast and it will slow down, and it dies. But in the nuclear case or in the atomic case, it is quantized. It can have 0, 1 speed, 2 speed, 3 speed, like that. So, it will have 0, 1, 2, 3, it is quantized. So, continuous is one thing, Another thing is quantized. Suppose I take one building, somewhat maybe 15-floor building. So I can be either in the first floor or in the second floor or third floor. I can't be in between the two floors. So that is called quantized. I can be in the first floor, second floor, third floor, etc. If it is continuous, I will be able to be present in any part of the building. That is continuous. But in the quantum picture, in the atomic and nuclear case, we see the angular momentum is quantized. Therefore, L we write as LH cross, where L is nothing but quantum number. It is called angular momentum quantum number. So m is mass of the nucleon. In the electron case, it will be mass of electron. Here it is the nuclear angular momentum we are talking about. So it will be mass of the nucleon. So L is the orbital angular momentum quantum number. So it is quantized, as I was just telling. It can be either 0, 1, 2, etc. Now here, when you say angular momentum, you should remember it is a vector quantity. So you can just remember as right hand thumb rule. If you take a right hand, so if the 4 fingers represent the direction of rotation of the particle, then the thumb will represent the direction of angular momentum. That you remember. Now suppose this particle that is moving is a charged particle, I will have angular momentum and also magnetic moment. If it is an uncharged particle, I will have only angular momentum. There won't be any magnetic moment. So we see that nucleon can spin and also it can orbit. The nucleon can spin and orbit. Therefore, we get, when it is orbiting, we get orbital quantum number L, and when it is spinning, we get the spin quantum number S, and L and S add up to give the total J. Suppose the nucleon is spinning and it is also orbiting, then it will have magnetic, it will have orbital angular momentum, spin angular momentum and orbital angular momentum, both, it will have both. So the addition, both are vectors. L is a vector, S is also a vector. Therefore, we get the total J as the total angular momentum. Since it is a vector, we have drawn the vector diagram. See, J equal to L plus S. L is in one direction, S is in another direction. I have to complete the parallelogram. S is in our figure, we have drawn S in the x axis and L is in some other angle. So if we complete the parallelogram, we will be getting the J value. Now we go to magnetic moment. Now both are, as already told you, if taking thumb rule, just take the particle which is orbiting along the 4 fingers, and the thumb will represent the direction of angular momentum. Now suppose the particle is chargeless, it will have only angular momentum. If the particle is having a charge and mass, so it will have angular momentum due to mass and it will have magnetic moment due to the charge. That is why we, along with angular momentum, we talk about magnetic moment. So now we consider it is orbiting, as we shown, like a right hand thumb rule, it is orbiting in one direction. This will be the direction of magnetic moment. So it's like a thumb rule. We take in this direction and this represents the thumb, and this is mu. Now here what we observe is any current in a closed loop in the electricity magnetism syllabus or any textbook, electricity magnetism textbook, we all of us know that if a current is flowing in a loop, it will produce a magnetic field, like we have the solenoid or current carrying a conductor, like that. Now here this is a nuclear case. So any current in a closed loop produces magnetic moment mu, and what is that magnetic moment? Mu is equal to I into A, where I is the current flowing and area. If the area covered is larger, we will have more current, where area of the loop and I is the current. So again, you just remember the right hand thumb rule. The figure that we have drawn is also corresponding to the right hand thumb rule. So if we consider P orbiting, that is proton, it is orbiting. Proton has positive charge. Therefore, the magnetic moment will be along the thumb. Suppose you take a negative charge particle, it will be opposite. Here this corresponds to, the figure that we have drawn corresponds to positive charge, direction of positive charge and direction of positive magnetic moment. Now here we have already equation 1, mu is equal to I into A. What is that current? Current is nothing but charge flowing per second and area is pi r square. So keeping that in mind, we go to the next equation. So mu is equal to E by T, because the charge of the proton is E and the time taken is, for one revolution, is T period, and the area is pi r square. So just I will go back, I into A. So this part is I. So this corresponds to I, this corresponds to area. R is radius of the orbit, T is the period. Now we can, because the period T can be written as 1 by T is frequency. So I get E into F pi r square, where F is the frequency, and frequency can be connected to angular frequency. Angular velocity is omega. Omega is equal to 2 pi f. We know that omega is equal to 2 pi f. Therefore, we get this final expression as this one, E omega but by pi r square. Now I will just go to the next one. We get the same continuation of that. Now what we are doing is, we are multiplying and dividing by m. Therefore, what will happen is, this m omega I can write as omega as Vr, because V equal to R omega. See, this is V equal to R omega. Therefore, instead of omega, I write this MVR. And what is that MVR? Already that is what we started. MVR is nothing but, MVR is angular momentum. That is the first equation. In the next previous section we saw that. So we get this LH cross. Therefore, if I substitute there, I will be getting the expression relating angular momentum and magnetic moment, because both are related, as we said. When it is orbiting, if it is a chargeless particle, it will have only angular momentum. If it is a charged particle, magnetic moment. So using that 3 in 2, so instead of MVR, we are writing as mu. Now here we have put one suffix there, L, indicating it is magnetic moment due to orbital motion. If it is magnetic moment due to spin motion, we will write as mu s. So we just write as mu L. So mu L is equal to EL H cross by 2m. This quantity we get. Now P has got positive charge, proton. Therefore, mu L will be positive. And neutron has no charge. Therefore, what will happen? Mu L will be 0, because it does not have charge. This part E, see this one, E is positive. Therefore, mu is positive for proton. And for neutron, mu E equal to 0. Charge is 0. Therefore, mu L equal to 0 naturally. So the nucleon also has a spin. Therefore, not only due to angular momentum orbital, also spin. Therefore, we write as mu s, mu suffix s, as E S H cross, where s is the spin quantum number, S H cross by 2m. So we get this second part here. Now again, P has got positive charge. Therefore, mu s equal to positive. Experimentally also they found out the same thing. Mu s for proton was positive. It was in agreement with this equation. If you substitute the mass and other thing, experimental value was in agreement. Now neutron has no charge. Neutron has no charge. Therefore, what we expect is, for neutron, E equal to 0. Therefore, mu s must be 0. But it was not 0. Mu s was negative. For neutron has no charge, but the magnetic moment was negative. So how do you understand this? Experimentally, magnetic moment is 0. That is because the neutron as such has got a positive core, surrounded by pi meson, negative pi meson. Therefore, as it spins, overall charge is 0. But when it is spinning, the minus pi mesons are spinning. Therefore, we get minus. So we will just continue this in the next class. But however, I would like to just brush up what we have done. So we just started with the binding energy curve, mass formula, binding energy curve and the stability, and we have just magnetic moment and angular momentum. How are they related? And generally, we will get that structure of neutron has got a positive core surrounded by negative pi meson. So, from this we will continue the next class. Now, we shall summarize what we have done today. So, we talked about binding energy and stability, and we explained how we get a fission process giving energy, fusion process giving energy, and we said about angular momentum and magnetic moment, and both are related. Magnetic moment and angular momentum, remember the right hand thumb rule, and the neutron, though it is chargeless, has got negative spin magnetic moment because neutron is surrounded by negative pi meson. Now, we will just we shall go for a few questions so that we can test our understanding of the subject. So, derive an expression for nuclear density and estimate its value. So, already we have been discussing this in the last class. So, we can do that. Obtain the expression for magnetic dipole moment. We have been deriving that from classical picture. You go to quantum picture and you can do that. And the third question is, explain why chargeless neutron has negative magnetic moment, and the crisp answer will be because of surrounded by negative pi meson, and draw the experimental binding energy curve, and we can show the stability, how fusion occurs and how fission takes place, and how fusion and fission gives liberation of energy. So, with this we will end this lecture, and in the next class we shall talk about mass formula. Thank you.